Okay, and sometimes what you'll want to do is you'll want to compare matrices. So here's what we're going to agree upon right off the bat. If you have two matrices A and B, sometimes you'll want to ask the question, are they the same matrix or not? Well, here's the answer. The only way they are is if, first of all, they have to have the same dimensions. So you have to have the same size, same number of rows, same number of columns, and every corresponding entry, you have to go through all their entries one by one and compare each of the corresponding entries and make sure they're all equal. And if a single pair of entries is different, then right away you'll just say the answer is no, the two matrices are not equal. So we're very strict. The only way they can be equal is if you literally write them all out entry by entry and they are identical in every way. Okay, let's look at an example of what I mean by that. Here's an example of two matrices. And somebody who, let's say somebody didn't read this remark, right? They didn't hear what I just said a moment ago, and you ask them, are these two matrices equal? Well, they might, first of all, they say, well, this one's a bit bigger, right? But then maybe you could convince them a little bit. You could maybe push back against that and say, yeah, but what about these extra entries? They're both 0, right? So who cares, right? You could make a case that maybe those entries shouldn't be important if they're zeros. But that's not what we're going to do. That's not the convention that we're following, right? Those zeros matter. Everything matters. And in fact, first and foremost, if you, strictly speaking, you wouldn't even get that far to look at those entries because you'd say right off the bat, this is a 2 by 2 matrix and this is a 2 by 1 matrix. So before we even look at their entries, their dimensions are already different. So you wouldn't even check the entries. Right away, you'd conclude that they are not equal. So these are not the same matrix. Okay, what about the next case? Well, now the dimensions are the same, right? This is a 2 by 3 matrix, and this is a 2 by 3 matrix. So if you want to ask the question of whether these two matrices are equal, you're going to have to look very, very closely through each of their pairs of entries. And what I mean by pairs of entries is, I mean, you look at this entry and look at this entry and make sure they're the same. Well, they're both equal to pi. So it's an irrational number, but that's allowed to be a matrix entry. So, but they're the same in this case. Here you've got a -2, and here you've got a -2. Okay, good. Keep on going, right? 0, we've got a 0, square root of 2, square root of 2, so far so good. 1, 1, 7. What's this? K. Looks like an unknown, right? If you assume that that letter K is being used to represent an unknown quantity, well, then the value of that unknown quantity K is going to be, that's going to be the answer, right? If it's equal to 7, then that value is equal to this value. But if K is equal to anything other than 7, then these two entries would not be the same, in which case the whole matrices are different, because that's all it takes is one particular entry in one particular position to disagree with the corresponding entry in the other matrix. That's enough for the two matrices to be different. So in this case, these will be equal exactly when these two quantities are equal. So, or in particular, when K is equal to 7. So we can say are equal exactly when K is equal to 7. So I choose the extra word exactly here to really be strict here. So if K is equal to 7, they're equal. But under no other circumstances are those two matrices equal. That's what we're saying. Okay, so I mentioned on the previous page that you can add matrices, and you can also subtract them, and you can also multiply them by scalars. I'm going to underline these terms in red, just for good habits here. And the way this works is exactly like it does with vectors. If you want to if you want to add two matrices together, well, they better be the same size, because you're going to need to add them together coordinate-wise. So they better have all the same entries in the same positions. That you got to have the right number of entries to work with. So we've got a 2 by 3 matrix here, and we're going to add it to another 2 by 3 matrix here. So the result is going to be another 2 by 3 matrix. So if you add two matrices together, they have to have the same dimension, and the result is going to also have that same dimension. So we'll add the 3 and the 7 to get 10. Then we'll add the 2 and the -5 to get -3. We got 4 plus 9 is 13. 6 plus 0, -2 plus 0, and then 0 plus -2. So that's going to be our result, right? So if for a moment, just pretend this had an extra row. Well, in that case, you couldn't do it. This would be undefined in that case, because the two matrices that you're adding together, it's going to turn out subtracting works the same way. They have to have the same number of entries. So if I added this extra row, 107 down here, the whole thing would not work and we wouldn't even proceed. So they have to have the same dimensions to be able to add them. And when you do add them, you'll have a result which also has those same dimensions, which in this case is 2 by 3. Okay, and the next example, we're going to multiply a matrix by a scalar. So just like with addition, it works the same in principle, works under the same, the essence of it is the same as with scalar multiplication of vectors. Just multiply each of the entries of the matrix by the scalar. So we'll just take each of those entries of that 2 by 3 matrix and we'll multiply them by 2. And just as before, the result is going to have the same dimensions here. So we're going to, I'll leave, for when I write down my answer, I'll leave space for 6 entries, 2 rows of 3 entries each, because that's how things are going to work. So I'll multiply each of these entries by 2. So we'll have 2, 2, and 2, and then we'll have 6, 10, and 14. Okay, so that's how you can multiply a matrix by a scalar. The third example here, we've got a subtraction example. So we've got a 2 by 3 matrix here, and we're subtracting another 2 by 3 matrix here, and the result is going to have the same dimensions. It's going to be a 2 by 3 matrix. So we'll just subtract each corresponding pair of entries. So for the first entry here, we're going to go 4 minus 2. That'll give us a 2 here. Then we'll go 0 minus 2, 5 minus 1, which is 4. Down here we'll have negative 1 minus 6, which will give us negative 7. 3 minus negative 1 is going to be 4. Right? And then 2 minus negative 12, that's going to be 14. Okay, and that's how we can perform the subtraction. Okay, so all of these matrices were 2 by 3. That's just a coincidence. That's a big enough size to get the idea across, but still small enough to be simple, so it doesn't take us half the class to go through just a handful of examples. But you can add or subtract or multiply by a scalar when you have matrices of any dimension. Just the only real important thing you have to remember about this is that if you're adding 2 matrices together, they have to have the same dimensions. If you're subtracting 2 matrices, they have to have the same dimensions. And in both cases, the dimension of the results are going to be the same as the dimensions of whatever your operands were here. In other words, the things you were subtracting or the things you were adding. Okay, and with scalar multiplication, well, you only have one matrix, so you don't have to worry about its dimensions. Just know that your result is going to have the same dimensions as the matrix factor. Okay, so these operations have some nice properties that we'll talk about for a moment here. So let's say you've got 3 m by n matrices. So really all that matters here is that A, B, and C have the same dimensions, because we're not going to reference m and n anywhere in these properties. But the important part to take away from this line is that whatever m and n are, that's the dimensions of all 3 of A, B, and C. They're not allowed to have different dimensions in the statement of these properties. And then R and S are just any real numbers at all. So the first property is that it doesn't matter the order in which you add up 2 matrices. So over here, for example, we had these matrices are written down in a specific order. Well, what would happen if I took this matrix and put it over here, and then I took this matrix and put it over here? So I added them up in the opposite order. Well, it wouldn't have changed the result. And in fact, it won't in any case. If you ever change the order of addition of 2 matrices, you don't have to worry about that changing the result. And the underlying reason is we're computing addition 1 entry at a time. And when you add corresponding entries, like for example, when we added 3 and 7 together, well, that's addition of real numbers. And in the case of real numbers, addition doesn't care about order. That's a well-established fact that you've been working with all through grade school, right? So, but the same is true. The same is not true for subtraction, right? Nowhere in this list of properties do you see A minus B is equal to B minus A, because that's simply not the case. Down here, if I were to change the order of these 2 matrices, I would change the result. In fact, I'd change it by a factor of -1 in each of the cases of the entries, but that's more detail than we need. The point is, this is true for addition, but not for subtraction. Okay, this is, by the way, you don't need to worry about this. This is called the commutative property of addition. And this is referred to as the associative property of addition. And you may recognize these properties are fairly similar to some of the properties we talked about in the world of vectors. And it's because the operations are defined so similarly. But what this is saying is if you want to add together 3 matrices, Well, you have to pick which two to add first, at least at a conceptual level, because addition is a binary operation. It takes two input arguments, and it computes one sum and gives you that back. So if you want to add up three matrices, well, you better pick which two you want to add first, and then you can add the result of that calculation to whatever your third matrix is. So this property is telling you, it actually, although you conceptually need to do that, it doesn't matter which way you choose, which two you choose to add up first, you're going to get the same result either way. So if I choose to add up A and B first and then add C to the result, or if I want to add B and C first and then add A to the result, well, then that would be it's guaranteed to give me the same result. Okay, so that's a handy property. So this is commutativity of addition, and this is associativity of addition. This is a nice property that tells us if we add the zero matrix to any other matrix, we're going to end up without making any changes, right? So if I have any matrix A at all and I add to it the zero matrix, I'm just going to end up with A still. A will be completely unchanged. And it makes sense, right? Because all the entries of the zero matrix are just zero. So based on how addition of matrices is defined, you're just adding a zero to every one of the entries of A, which is not going to change any of those entries. So it's no surprise that you just end up with A back. Okay, and here this says that scalar multiplication distributes into addition, in the sense that I can write arrows here, kind of like I'm foiling, right? If I want to add two matrices A and B and then multiply the result by R, that's what this is describing. On the right-hand side, this is saying I'm just taking each of the matrices A and B and multiplying them by R separately and then adding them together. Well, this property says you're going to get the same thing. So in ordinary language, this is just saying that scalar multiplication distributes into addition. And this is saying that scalar multiplication itself distributes among scalars. So if you have two scalars, R and S, remember R and S are just real numbers here, not matrices. So if you have two scalars, R and S, and you want to add them together and then multiply the result of that calculation onto the matrix A, so that's one scalar multiplication. It turns out you can multiply each of the scalars R and S onto A separately and then add the results, and you'll get the same thing. So there's going to be situations where this is more convenient than this. So you may go in either direction. There's neither one of these forms. In both of these cases, neither of the forms on either side of the equations are necessarily inherently better than the other, but certain situations will make it so that one form is more convenient than the other. So it's nice to be able to move back and forth between them. And then the sixth property here, what if you want to multiply two scalars onto a matrix? Okay, well, if you've got two options. One is you could multiply each of them onto the matrix separately, one after the other. So first multiply S onto the matrix A, and then whatever you get as a result, multiply R onto that. That's what the left-hand side of this equation is describing. But on the right-hand side, there's only one scalar multiplication happening. The R and the S at first are being multiplied together with just ordinary real number multiplication, because R and S are real numbers. So you multiply them together, that's nothing new. That's nothing to do with matrices. So the result of multiplying R and S is going to give you another real number, which you can then multiply onto the matrix A. So that's your only scalar multiplication. But again, just like these other properties, they're telling you that both of those calculations are guaranteed to give you the same result. Okay, so what do we have? We have addition, subtraction, and scalar multiplication. And that the word scalar is important for the scalar multiplication, because what I'm referring to up here, because think about this example. We're not multiplying two matrices here. We're multiplying a scalar by a matrix. Here's this, one of the factors is a scalar, and the other factor is a matrix. But what some of you are probably wondering by now, because we've certainly waited long enough to bring this up, but what about if you want to multiply a matrix by another matrix? Well, we've talked about it a little bit in the specific case where one of your factors is a vector. And as long as it has exactly the right number of coordinates, we've been able to make sense of that by giving it a definition. But what we haven't talked about is the general case where you have the product of two different matrices and how you actually write that down. So that's what we're finally going to define now. And it's closely related to the definition of multiplying a matrix by a vector. And in fact, we're actually going to refer to that definition here. Okay, so here are the assumptions you need to make in advance. So let's start by assuming that A and B are matrices, so that's not very strict, but what is strict is their dimension requirements. So notice that I've used m by n to represent the dimensions of A, and I've used n by p to represent the dimensions of the matrix B. So the n appears twice. You'll see n as the number of columns of A, and then you'll see it again here as the number of rows of B. That's the essence here of our assumption, is that the number of columns of A and the number of rows of B have to be the same. That is necessary and sufficient conditions for the product A times B to be defined. And the order of the factors matters here. So A is the factor on the left and B is the factor on the right. And we will talk more about that coming up on the next page. But for now, let's say, well, what's the actual definition? Well, first, we're going to separate the matrix B into columns. Okay, so if it's n by p, that means p is the number of columns of B. So we can write B as a row of column vectors, B1, B2, all the way up to BP, where each of those column vectors has exactly n coordinates. So this is an n-dimensional vector, this is an n-dimensional vector, and this is an n-dimensional vector. Where am I getting that from? Well, B has n rows. So the number of rows of B is going to tell you how many entries each of these columns has, since we're writing it as a row of columns. Okay, once you've done that, this is how you can define your product, A times B. And you're going to define it as a row of columns. But the columns here, notice the first column of AB is the product of A and the first column of B. That's where this came from. So take the first column of B, multiply it by A, and that's going to be the first column of A times B. Then take the second column of B and multiply that by A, and the result is going to be your second column of the product of A and B. And do this all the way until your very last column of B, and you've multiplied all the columns of B by the matrix A, and then you put all those columns together to finally get your product, A times B. And you might pause and say, yeah, okay, well, this is a circular definition. The whole point of this was to tell me what the product A times B is and how to actually evaluate it. But what's this? It looks like we're depending on the definition of a product here. A needs to be multiplied onto B1, needs to be multiplied onto B2, and it needs to be multiplied onto BP. But if we're defining the product here, then how is this not circular? How does it not just beg the question and not actually answer it? Well, in this case, this is a specific case where you're multiplying a matrix A by a column vector. And same with each of these products, they're all of the specific case where your right-hand factor is a column vector. So that's something we've already talked about. We've already talked about how to multiply column vectors by matrices. So we already have a definition for that, and we're taking full advantage of that. So in case you've forgotten that, well, it's important to review, right? So that's why review is particularly important in this class. But the good news is I'm going to remind you on the next page. Okay, so let's take a look at an example.